Let's continue our lesson on oxidation and reduction reactions. We commonly call those redox reactions. Top of page 12 in our note pack is where we're looking. We're going to start working some examples of reactions that fall under this big umbrella called redox reactions. Remembering that what they all have in common, all these kinds of reactions, be it a combination reaction, could be a decomposition, could be a single replacement, and it could be a combustion pattern, not the double replacement. All of these four patterns fall under this large umbrella called a redox reaction. And what that commonality is between them is how they change charge. When reactants form products, we'll see that there have been a change in their oxidation state as reactants go to product. Now let's take an example of a combination pattern first. So a familiar pattern of a combination. Suppose we have a metal, Na for sodium, and it would be in a solid state, reacting with the elemental form of chlorine, Cl2, it's a molecular element, and it is in nature in the gaseous form. The pattern of chemical change for a combination reminds us that when a metal, such as sodium, combines with a nonmetal, such as chlorine, they're going to form an ionic compound and they're going to hook by charge. We had studied this very much in depth in our first year chemistry. They form a compound, an ionic compound, commonly called a salt, sodium chloride. Sodium with its plus charge, chloride with its minus, we get NaCl. Now remember, when we studied the 6 rules for assigning oxidation states, any element in its natural form, such as sodium, has an oxidation state of a 0. Chlorine, found in its elemental form as a molecule, has an oxidation state of 0. Now when they hook together, notice now how they're carrying a charge. The oxidation number of sodium is +1, and the oxidation number of chloride is -1. Sodium changed charge. It started as a 0 and became more positive. Chlorine went from a 0 and became more negative. We've had a transfer of electrons. Now let's go ahead and balance this. We'll need a 2 in front of each of these. So 2 NAs plus Cl2 makes 2 NaCls. You'll need to adjust that coefficient in your notepad page. So we've had a transfer of electrons. When sodium became more positive, let's show this. Sodium started at 0, became more positive. Now what has happened is it's lost 1 electron. Notice how a +1 charge, when added to the negative charge of an electron, gives me the 0. So the charges on both sides of our arrow are matching. They're both at 0. When chlorine started at 0 and went over to chloride, -1, well, it had 2 units of -1, we're going to see a total of 2 electrons being lost there. And you can see why we distributed the coefficient of 2 in front of each of the sodium, so that the number of electrons lost equals the number of electrons gained. We're going to practice this half reaction method multiple times. What we've just done is split the oxidation and reduction into 2 halves, the half reactions. We can label this process as oxidation and this process as reduction. The oxidation is a loss of an electron. Reduction is the gain of an electron. In this combination pattern, we saw sodium and the chlorine change charge, and they did so through the process of transferring an electron. Let's take a peek at a second pattern that's very familiar to us, called a combustion pattern. When a hydrocarbon combusts, our pattern of chemical change, let's take an example of a simple hydrocarbon called methane, CH4, adding oxygen, and a whole bunch of heat and light are produced along with carbon dioxide and water. Here is the skeleton of our combustion pattern. Let's go ahead and take a minute to balance. 4 H's, I think we'll need to double the water. 2 and 2, we'll need to double the oxygen. So here's our balanced combustion pattern. Now how might this also be labeled as a redox reaction? What has changed charge? Well, let's take a minute and use those 6 rules to identify what are the oxidation numbers of each of the elements. Here's an element in its natural state, molecular oxygen. Any element found in its natural state is assigned a 0. Over here, hydrogen, this is rule 4, I believe, hydrogen is attached to a non-metal, making it a positive 1. Carbon would have to be a total of a net 4 to sum to equal 0. 4 units of a plus 1 balance a negative 4. How about on this side? Oxygen's always a minus 2 unless it's a peroxide, but it is not here in this carbon dioxide molecule, giving me a total of negative 4. So carbon must be a positive 4. Hydrogen's plus 1, minus 2. So what has changed? Well, right away I noticed that oxygen started at a 0 and became more negative. It has gained electrons, becoming more negative by taking in more negative electrons. Carbon on the number line went from negative 4 all the way to positive 4. When you become more positive, you've lost electrons. Of course, the hydrogen did not change, and oxygen could have gone to either place. I could have gone either way, and saw that it changed from 0 to minus 2. So with our very first exposure to redox reactions, we looked at a combination pattern and we looked at a combustion pattern. Both of these have a larger umbrella called a redox reaction that describes any type of reaction where charges or oxidation numbers change on an element from the left to the right-hand side are now going to be called combustion. So oxidation, that term oxidation, means an increase in the oxidation state, an increase becoming more positive on the number line. You do that by losing those negative electrons. Take away a negative particle and the resulting species is more positive. The term reduction means to reduce your oxidation number. You become more negative, and you do that by gaining those negative electrons. There's a little saying that helps me remember oxidation and reduction. Some teachers I've heard use the term oil rig. Oxidation is loss, reduction is gain. However, the one that I've always used is Leo and Grr. There's a funny little sentence. Leo the lion says grr. Leo, loss of electrons, is oxidation. Loss of electrons is oxidation. And grr, the gain of electrons, is reduction. Something that is oxidized has increased its oxidation number on the number line by becoming more positive. Something that is reduced has gained electrons and becomes more negative on the number line. Now, just to make this a little bit confusing, and I apologize for doing this, but we've got some vocabulary associated with this, and it is confusing at first, but kids will eventually kick it in. We have the term agent to describe. So let's go ahead and fill in the blank. Oxidation means an increase in oxidation state. Reduction means a decrease in oxidation state. But up here where it says, and I'll go ahead and show the slide, the substance that is oxidized is called the reducing agent, and the substance that is reduced is called the oxidizing agent. Go ahead and fill those blanks in, and then let's go down and kind of give some clarification to those vocabulary words. Remember in our previous example where we had sodium atom losing an electron, and we wrote this out as an oxidation half reaction, a loss of an electron. Because sodium is being oxidized, it is called the reducing agent. The term agent means it's forcing the other reactant to become reduced. We had chlorine gaining 2 electrons. Let me add that back in correctly. Gaining 2 electrons to form 2 units of chloride. Notice the charge on both sides of our arrow are the same. They don't have to be a 0, but they have to be the same. -2 is the charge on the left, and -2 is the net charge on the right. This was called a reduction half reaction. The gain of electrons is called reduction. But however, chlorine is now going to be called the oxidizing agent. Chlorine forced sodium to be oxidized. Sodium forced chlorine to be reduced. So it's really just a matter of flipping the word when you add the word agent. If you're asked to find the reducing agent, really it's another way of asking you, what was oxidized? If you're asked to find the oxidizing agent, it's just another way to ask you, what was reduced? Very important. I would put this little highlighted note in your notepad page, the term agent. Very important to process the term agent and then the vocabulary associated with it. Agents force the other reactant to do the opposite of what it has done. Wherever we've had an oxidation, we must have a reduction. Reducing agents is the substance that was oxidized. Oxidizing agents is the substance that was reduced. By the way, a good another note, agents are always reactants. Let's go on and take a peek at the next slide. The term agents, I'm just processing this a little bit more. Oxidizing agent gets reduced. It gains electrons. More negative oxidation state. By gaining electrons, you're being reduced. Reducing agents gets oxidized. You lose electrons and become more positive. An easy way to remember that, Leo the lion says grr. Losing electrons is oxidation. Gaining electrons is reduction. Oxidation becomes more positive. To be reduced becomes more negative on the number line. Traditionally, this term agent gets confusing for beginning students, but as I said, just with a little practice, it becomes quite easy. Let's identify the oxidizing agent, reducing agent, the substance that were oxidized, and the substance that were reduced. And we'll just use these following examples, and these are typed out in your notepad page as well. So let me kind of come down and we'll write these out one at a time. Here I have elemental form of iron, FeS, with the elemental form of oxygen, O2 gas. And it's a combination pattern forming an ionic compound, Fe2O3. We'll take a minute to balance this. There we go. Now I know from first year chemistry this is called a combination pattern, but now under this larger umbrella it will also be defined as a redox reaction. Always begin by identifying the initial states of their oxidation numbers. The elemental form of any atom is 0. Iron, oxidation of 0. Here's the elemental form of oxygen, assigned as 0. Oxygen is a -2. Iron becomes a +3 if I simply just uncrisscross this ionic compound. So here I have had iron go from a 0 to a +3, and oxygen went from a 0 to a -2. Iron became more positive, didn't it? The loss of electrons is oxidation. Oxygen became more negative. the gaining of electrons is reduced. Remember the term oxidation, what was oxidized, what was reduced, what are the agents? Always come from the reactant side. Iron was oxidized, and therefore it is the reducing agent. And can I just write RA and we'll get that clear? Reducing agent. Molecular oxygen was reduced, and therefore it is the oxidizing agent. Should we try another? Here we have Fe2O3, iron 3 oxide, that's in solid form, reacting with gaseous carbon monoxide, and it forms liquid iron and 3 carbon dioxide units in a gaseous form. Did I miss the coefficient? I sure did, right there. A 1:3:2:3 stoichiometric ratio. We're being asked what's oxidized, what's reduced, and then to identify the agents. So step 1, we better figure out what the initial oxidation numbers are. We just worked this guy. Oxygen's always a -2, ion crisscross here, iron's a +3. If oxygen is a -2, carbon must be a +2. Elemental form of iron, here's 0. Oxygen's always a -2, gives me a total of -4, so now the carbon has gone to +4. Stand back and look. What's changed in the charges? I noticed iron went from a +3 to a 0. It's going down on the number line. It is getting reduced. Grr, gaining electrons, making it become more negative. Carbon started at +2 and went to a +4. That's becoming more positive. Losing electrons is oxidation, making the element become more positive. So identify what was oxidized and what was reduced. The reactant of Fe2O3 is the oxidizing agent because iron was reduced. And I'll just use that symbol. The second reactant, gaseous CO, is the reducing agent because carbon was oxidized. I'll give you a moment to process that. We started this journey by just simply assigning oxidation states. With one becoming more negative, there must be going the opposite direction. Carbon became more positive. We have to have one of each. Notice how I grabbed the entire reactant to identify the agent. It's not just iron, it's iron oxide that's the oxidizing agent. It's not just carbon, but it's carbon monoxide that's the reducing agent. I take the entire reactant's formula to identify the agent, and then in that I describe what the element was that changed charge. Here's that last example. In this one I have a little adjustment to make. Could you please make sulfite the polyatomic ion, but it actually carries a -2 charge. In my notepad page I only have it listed there as a -1. Please make that adjustment. We're going to have that with a hydrogen ion, which is a +1. A permanganate ion, which is MnO4 -1, polyatomic ion. Make the same adjustment here. Here's sulfate, but it carries a -2 charge off our polyatomic. We have a water and then a manganese +2. Alrighty, what's change charge? Well, let's start by assigning all oxidation numbers, and these should go pretty fast the more we practice. Starting with the oxygen here, I know it's a -2, so therefore the net negative is -6. It's a polyatomic ion carrying a -2 overall. We made that adjustment there in the note pack. So sulfur must be a +4. Here's a monoatomic ion, so it matches the charge of +1. Oxygen is a -2. There's 4 of them. So manganese here must be starting at a +7. Let's do the product side. Oxygen is always a -2, so I'm now at a total of -8. Sulfur must be a +6. Here's an easy one, +1 -2. And a monoatomic ion matches the charge, so manganese now at a +2. What's changed? Here, sulfur was a +4. It increased on the number line to a +6. It was oxidized. Losing electrons make you become more positive. Here's the manganese. Started at a +7, went to a +2. It was reduced. There's the GR part of our half reaction. Gaining electrons is reduction. So let's identify. Sulfite, SO3-2, because it was oxidized, is the reducing agent because sulfur was oxidized. The permanganate ion, MnO4 -1, is the oxidizing agent because the manganese was reduced. Let's pause our work here and give you time to process. How do we assign oxidation numbers? If you're not doing that quickly from the previous video, that's really worth practicing. That's a solid skill that's going to lend yourself in figuring out what was oxidized, what was reduced, and how do we identify the agents. When you've mastered those vocabulary terms, identifying, just as we did in these 3 examples, work to master those, then you're ready for the next part of your lesson.